Igor Khavkine, is that the right pronunciation?
Good enough.
Close enough.
Yeah.
From Utrecht is going to basically tell us how to discover gauge invariant observables in classical and quantum gravity.
Okay, thank you. So first I'd like to thank Steve and Nika for extending the invitation to visit Davis. It's a very nice place. And I hope to dazzle you with some my semi-recent work. This is sort of the outline. First I want to tell you a bit about the motivation for why I'm doing this, and more or less what paint a picture of what I want to do. And then I'll describe a particular gauge invariant observable that I call the time delay. And I'll discuss some of its properties in classical gravity, its relation to causality in particular, and also how it can be treated in perturbative, or rather in linearized quantum gravity. And then I'll summarize. Okay, so here's a question that someone who works on quantum gravity has already spent a lot of time thinking about. If I had a theory of quantum gravity, what would I do with it? So I mean, a lot of people are trying to get the theory for that, but what is it good for? I think the answer is actually quite simple. And it should be independent of whatever model that people come up with, because it should describe our universe somehow, and our universe is, it doesn't really care which model people find favorable. And the answer, I think, is this. So I should use it to compute both qualitative and quantitative quantum gravitational corrections to whatever experiments and observations that where these corrections are held. Unfortunately, if you think about this verb here, to compute, and you think about what people actually compute in whatever model of gravity that they're working in, the things that are easiest, often what people compute are what is easiest to compute, what is most accessible. Those things are not always necessarily relevant. They may have interpretation within the framework or the theory, but sometimes they're difficult to connect to direct kind of experiments. Okay, so one idea is to work backwards. So if you want to compute something that's worthwhile, start with a potential experiment that could just, in principle, be done. Maybe it's a bit too early to worry about practical, costly, cost-effective realization. Just something that's possible in principle. Describe the experiment operationally. So in essence, it becomes a thought experiment. And construct a precise mathematical model that describes the output of this thought experiment. And this will be your observable, right? They should have some mathematical expression or model for it. And because you started with this thought experiment, it has an unambiguous interpretation that comes with the mathematical expression. And moreover, if this is done really at an operational level, so you're essentially describing experimental protocol. This experiment could be modeled in different variants of quantum gravity, and because of the fixed interpretation that comes with this experimental protocol and the resulting mathematical model of the corresponding observable, if you could do the calculation in different frameworks for quantum gravity, you could essentially compare. Right? Because often, because of the mathematical structure of different theories are so difficult, so different, they may be difficult to compare directly. But if you keep fixed physical interpretation in mind, this makes the comparison easier. Okay, that's a bonus if you can actually get somewhere. So, which experiments or experimental protocols should we concentrate on? So, which are the ones that are sensitive to quantum gravitational effects? Kind of easy but true answer is that all of them are, because everything is coupled to gravity. Okay? Unfortunately, we don't necessarily know in advance which experiments will be most sensitive, right? Because there are quantum gravitational effects everywhere in this room. We just don't see them. Right? But if we look in the early universe, maybe there is something that we have a hope of seeing with cosmological experiments. However, the state of the art of dealing with observables is a bit dismal. So let's not get too ambitious, and let's just learn how to model as many experiments as possible. Okay, and then among those, try to look for the ones that may be most sensitive to quantum gravitation effects. So I will be thinking about at this level rather than trying to find the most sensitive experiment to think of. Right? And the reason I think this way is because there are lots of surprises. People find surprises in physics all the time, and we can kind of try to make a guess at what might be most important, but sometimes we can be wrong. So I think it's safe to just start with something easy, or more or less easy, but still grounded in some kind of easily interpretable thought experiment, but also something that would lead to interesting results. All right, so what is the thing that I'm proposing to look at? Okay, here's the thought experiment that I submit to you, and I think it is, well, it has several advantages. It is simple in a certain way, it has some simplicity to it. It can be treated quite easily in classical gravity. One can do some calculations with it, approximate calculations in quantum gravity, which I'll get to later. And it has interesting, so the results of such an experiment have an interesting connection with causal structure in space-time. And I find causal structure in gravity, both classical and quantum, very interesting. So if you find that as well, then this kind of observable should be interesting for you. All right, so what is it that is displayed in this picture here? For an operational description of this experiment, I need more than just gravitational degrees of freedom, pure gravity. I need a little bit of matter, which will include in a model of corresponding to the measurement apparatus. Right, so I'll try to describe explicitly what I'm going to do. Right, so consider some ambient space-time, and in that space-time there are two localized systems that I call the lab and the probe. So the lab, each one travels on geodesics. So this is the lab geodesic, the vertical one, and the probe geodesic is the one that comes here at an angle, and they intersect at a certain point O. So if you want to think of it visually, this could be a spaceship, and this could be a point where I open an airlock and throw up some object, the probe, outside, and they travel inertially with respect to each other. So the probe has some initial velocity with respect to the laboratory. Right? Each of these objects carries a proper time clock, which ticks at proper time rate along each of these whirl lines, and say they're synchronized at the ejection point, at the point O. Okay, the probe has some instruments on it, like besides the clock, it has also a radio transmitter, and what it does is it periodically sends out signals that are time-stamped with the emission time. Okay, so for example, at the point P, the signal is emitted. So the signal travels at the speed of light. So that travels along the non-geodesic here, and it's received at by the laboratory at this point Q. Right? And so let me call the reception time, proper time in the lab system S for the signal, and the timestamp that is carried by the signal tau. Right? So I wrote this here tau of S because the laboratory, what it does is it tabulates at each particular reception time. There's a certain timestamp, right? So you can plot reception time, timestamp versus reception time, and you get some curve. And this curve is going to be tau of S. Okay, and what I'm interested in, what I call the time delay observable, is this difference here. So I take the reception time, I subtract the emission time, I call this delta tau, and this is the time delay curve. So now I'm going to argue that what I just defined here, this time delay, is a physical observable. So I gave you a protocol, and I can show that I can associate mathematical expression for it in theory of gravity with this laboratory included there, and that's invariant under diffeomorphism, which makes it a physical observable. I'll be talking about the time delay and the emission, the emission time, more or less interchangeably, because they're just different by this quantity that is in our control. It's, the reception timeness. Okay, so let me just quickly run through the argument. It says that shows that the time delay is gauge invariant. So first, I need to define precisely what I mean by a system with gravitational and laboratory degrees of freedom. I introduce an idea that I call, concept I call lab-equipped spacetime, which consists of this tuple, a manifold, a metric, Lorentz metric on it, some technical conditions, a special point, which corresponds to the ejection of the probe, and a tetrad. So at the ejection point, there is a special direction, which is tangent to the probe, the world line of the laboratory. And then there are also 3 spatial vectors that determine the direction in which the probe is thrown. Okay. And here's the notion of gauge equivalence between, say, between a pair of lab-equipped spacetimes. So there's one tuple and there's another tuple with primes. If there's a diffeomorphism from M to M prime, such that the metrics are mapping to each other, so it's an isometry, as well as the special points, O marked by O and O prime, are mapped into each other, and at that point the frames at point O, the special frames are also mapped into each other, then I say that these lab-equipped spacetimes are gauge equivalent. Okay?
So is the condition of the frame only at the point O, or every?
So the frame is only at the point O.
The frame is only at the
Yeah,
point O.
that's right.
And but you're not allowing local Lorentz transformations.
Well,
Well, I guess
what
it's
would they
only
do?
at one point.
Yeah,
That
yeah,
that's
that's right.
a diffeomorphism.
So if you think of a spaceship, I mean, you could have special marks saying like this point is west, this is north and south, and then you say, okay, I'm going to throw the probe in the southward direction. So this is the only place where this frame is used
Okay.
in my setup.
Okay.
Okay, so these observers or lab and probe world lines are geodesics that are defined using the data that I introduced in lab-equipped spacetime. So these are both geodesics that pass to the point O with different tangent vectors. The time-like element of the tetrad gives you, like I said, the tangent to the lab world line, and then which was what I was just saying before to Steve, the tangent to the probe world line is a linear combination of these frame vectors, spatial frame vectors. Well, I mean, it's a linear combination of the frame vectors with some predetermined coefficients. So when I describe the experimental protocol, these numbers here, they're just pure numbers, and they go into the description of the protocol. Okay. The signal is another geodesic. It's a null geodesic that leaves the point P, which is a certain distance, proper time distance T from the point O along the probe world line, and then it intersects the lab world line at point Q. This is the reception time. And you just draw the geodesics, and then you find a null geodesic that intersects both of them in this way. And then once all this data is defined, the observable is then going to be this tau. So if you go back to the picture here, and if I specify 2 points here, so any arbitrary 2 points, I can always draw a geodesic between them. And I want not, and these points are labeled by proper times from point O. Most of them are not connected by null geodesics. So those that are connected by null geodesics correspond to the pairs of emission and reception times. Right, so once I fix a reception time, S, which again goes into the definition of the experimental protocol, the emission time becomes a function of it, and as well of the reception time and the ambient geometry. Okay, so this is how I define the emission time, tau of S, and the time delay is just an inference. Okay, so a theorem, the observable I just defined, is gauge invariant. Right, so if I take two lab-equipped spacetimes that are themselves gauge invariant, and for both of them are compute the time delays, so for one I call it delta tau, the other one delta tau prime, as long as these two lab-equipped spacetimes are gauge equivalent, these numbers are equal. And that's precisely what it means to have a diffeomorphism observable, and the proof is pretty simple, it's by construction. Right, so if you read the literature on observables and gravity and you run across a statement like, oh, we don't know very many examples of observables in gravity, this statement is, it has some meat to it, but often it only holds if you constrain yourself too much. So if you, for example, consider pure gravity without any other degree of freedom whatsoever. Right? I think what is easy to see from this discussion is that if you add a little bit of extra degree of freedom that are well motivated by operational considerations, the situation becomes much better. So you can think of 100 different experimental scenarios, and then you can associate observables to them in a similar way. And then you have a rich family of gauge invariant observables to them. Okay, so this is the kind of conceptual idea that I want to impress.
Yeah, usually what people say is that we don't know any local observables, and
yes.
This is certainly not a local.
True, absolutely true. But if life gives you lemons, you make lemonade.
Yeah.
So, I mean,
Sure.
you just have to work with it. You have to learn to work with these kind of observables.
So, technical question,
Yes.
Are you constrained to a small enough region that you don't have to worry about caustics here?
I worry about that from time to time, and the last time I worried about this was a while ago. So I think it doesn't matter so much. But it certainly is easier when you're in a small region without any caustics in geophysics. Well, at the very least, the explicit calculations that I've done are all in perturbation theory, where caustics don't show up. So maybe if you really go to some kind of highly nonlinear regime, you might have to worry about it, but that's for future generations. Or at least me in a few years to worry about. Okay. As I hinted at earlier, once constructed, this gauge invariant observable is not interesting just by virtue of being an example of that, but it also encodes some information about the causal structure of an ambient spacetime where you're doing the experiment. Okay, I'm going to explain how that works. So it's easier to kind of, well, for this particular slide, it's easier to think of the emission time rather than the time delay. This emission time satisfies certain inequalities that are tightly linked to the Lorentzian character of the ambient spacetime. So, and you could define the same kind of setup in a Riemannian manifold, but similar inequalities will not hold. So that's why I say that these inequalities are tied to the causal or Lorentzian structure. So there's one of them that comes from the fact that in the Lorentzian spacetime, nothing can travel faster than the speed of light. Okay, and what this translates into here is that if you have two emission events that are one after the other, the reception events are always in the same order. Okay, so if one could travel faster than light, and the geometry was sufficiently complicated, then you might have a situation where an earlier signal gets outpaced by a later signal, and you have an opposite ordering at reception. But in Lorentzian spacetimes, this does not happen, and I have a proof in my paper. I'm not relevant, but it follows from some propositions in some Khavkine analysis or some other book in Lorentzian geometry. All right, so there's a bound. So this may not be particularly useful bound locally. Another way to look at it is that the emission time always has a positive derivative with respect to the reception time. So you can think of a bound on the derivative here. So it's greater than this one.
Again, technical question.
Yes.
You must be requiring something like global hyperbolicity here, or some global condition.
Yes, so
Otherwise
definitely
some
no
wormhole.
closed time like curves.
Yeah.
So
Okay.
I think, yeah, global hyperbolicity definitely gives you.
Yeah.
But the conditions are surprisingly weak.
Really?
So I was a bit surprised when I when I wrote down the proof and I only needed a certain basic assumptions. I would have to check again precisely what the assumptions are. It's in my paper. Right. Another bound comes, well, I call it the twin paradox bound. So it has to do with the fact that in Lorentzian spacetime, geodesics have maximal length. Okay, so I got 2 points here, point O and point Q, and there are two curves that join them. So there's the geodesic one, and there's this broken geodesic one, which gives, so there's the lag-word line and the pro-word line followed by a signal. And twin paradox essentially tells you that the proper time along this curve is going to be greater than along this one. Right, so it's a little bit tricky because this is a null segment and not a time-like one, but you can essentially adapt the proof so the general proof that tells you that this is in fact the case. And again, following some propositions of Khavkine analysis, for example, you could write the emission time as a sum of the absorption time, so the reception time, together with this kind of integral, where you use some auxiliary curves that interpolate between this one and that one, and you can show that this is always negative. Okay, so then this gives you the desired inequality. So this gives another bound on the emission time or the time time. And these two bounds, the bound from the maximality speed of light and twin paradox bound, I call them causal bounds, again because they have this strong relationship to the Lorentzian character of the geometry that we're considering. And this will come up a bit later while considering the question whether the same bounds can hold in the quantum theory or not. So I'll leave you in suspense for a bit. I'll get back to it. Soon after telling you how to, I gave you this very nice abstract description of these observables, but the idea I started with is computation. So can we do any calculations, practical calculations with this observable, and get some physical results out of it? This is very difficult because this observable is defined so abstract. But what is manageable is perturbation theory. So if we start with, if we consider only metrics that are weak perturbations of Minkowski space, so you can write every metric in the class as Minkowski metric plus small perturbation, then we can find an explicit expression for the emission time as a function of the perturbing metric. You can think of it as a graviton field. The expression has this structure. It has a zeroth order piece, and it has a first order piece, and of course it will have high order pieces, which I not considered. So S appears here as a parametric dependence. The dependence on the metric perturbation appears inside certain linear operator. This linear operator, once it's properly normalized, I call R operator. And it's a sum of two terms. Each term is a somewhat complicated integral differential operator that involves derivatives of the H field, and also integrals of some components of it along the background geodesics composing the triangle that we're trying to describe here. So if you ever try to solve the geodesic equation perturbatively, you would already have a feel for what the structure of these terms is. I won't give you the exact formula, it's a bit complicated, but I'll say a bit about the general structure of these terms later. What I want to point out at this moment is that because this expression is gauge invariant, the linearized expansion, so the linear piece, is expected to be invariant under linearized gauge transformations. And in fact, this is the case. You can explicitly check it. What was a bit surprising to me is that when you decompose into these two pieces, each of the pieces is also invariant under linearized gauge transformations. And I think there's an important lesson here. So suppose that you had a different program for dealing with observables. You just come up with some mechanical way of generating all possible diff-invariant expressions, or invariant under linearized diffeomorphisms. You would probably discover the expressions for H and J separately, maybe together. But how would you be able to assign physical interpretations to them? So here this problem doesn't appear because I already start with physical interpretation, which is associated with this emission time. And then all the rest of the steps are really purely technical. And it just happens that I find that the result is written in terms of this combination. But if I only had these individual pieces as output of some program to generate all different variant expressions, I wouldn't really know how to assign an interpretation to them. And I think this just illustrates the value of starting with some kind of thought experiment in mind before thinking of observables at a very technical level. Okay, so I've told you how to deal with this observable in classical perturbation theory. Now in fact, classical linearized gravity. Now I'll jump directly to quantum gravity. What is quantum gravity? So everyone has their favorite theory. I think being very conservative, what one can say is that in some regime, particularly the low curvature regime, or weak deviations from the Minkowski space, gravity is expected to behave like a field theory. Especially if you concentrate at the linearized dynamics of this theory, they're quite well understood. I mean, this is where the theory of gravitational waves lives at the classical level. But being in linear field theory, it's also true that we understand the corresponding quantum theory quite well. Right? So, and I think that if you consider the argument that any harmonic oscillator that we've encountered in nature and have been able to examine both the classical and quantum behavior, the quantum behavior is captured by the Fock quantization of the harmonic oscillator. Right? And if we think of the gravitational field as a collection of harmonically oscillating modes, then so with of weak amplitude about Minkowski space, then it is also, I think, fair to assume that the quantum gravity in this regime, with weak curvature, small deviation from Minkowski space, will also be described by the quantization of linear gravitational field. So with this in mind, I think this is a fairly conservative but valid approach. Not thinking of anything extremely fundamental, but not thinking necessarily about what happens to the rotation degrees at the Planck scale. We can start with this theory and then just compute and see what we get from considering this observable. One thing that's missing from linearized quantum gravity is these degrees of freedom associated to the laboratory and the probe. Because they are not described by quantum fields in our classical model, they're described by these world arcs. So how do we incorporate that into the description? So my suggestion is kind of taking an easy way out. So let me skip ahead. When you consider the expansion for the emission time, it has the zero order term, then it has a term that's linear in the graviton field. All the dependence on the experimental apparatus enter into here. Okay, and that dependence is encompassed by the zeroth order geodesic solutions on Minkowski space. So I think that it's valid to, in some limit, ignore all the possibly complicated quantum effects that come from the internal dynamics of the experimental apparatus, and then just think of them as being reduced to these background geodesics in Minkowski space that enter into the definition of this operator here. So it's not strictly true that there are no contributions to this quantity from the internal dynamics of the experimental apparatus, but there's actually quite a large literature in considering quantum corrections to clocks or motion of particles and so on, going back to the early work of Saliker and Wigner back in the 60s or so. But none of these works have considered corrections coming from purely gravitational degrees of freedom. So what I'm thinking of here is of ignoring the corrections that come from internal dynamics of the experimental apparatus and concentrate purely on the corrections that come from the gravitational degrees of freedom. Right. So this is the working assumption that I made here. And one more comment is that this quantity is diffeomorphism under transformations of Labiquid spacetimes. So if you were to fix the special point O and the frame at that point to some particular values, then the remaining freedom gauge freedom has to respect that. And so you will only expect this quantity to be invariant under diffeomorphisms that fix the special point O and the frame at it. But so the remainder of the gauge degrees of freedom that you should consider in gravity diffeomorphisms is then the point correct transformations that move this point around and transform the frame. But it so happens that we do perturbation theory around Minkowski space, and I will specifically choose the point correct invariant Fock space to do the calculations, which are in fact invariant under the remainder, this remaining transformation group. So it turns out that this expression here is invariant not only under linearized diffeomorphisms that fix the point O on the frame with E, but are also invariant under arbitrary linearized gauge transformations. So it's a bit of a technical point, but these components will, this data will not really appear anywhere else except in the definition of this linear operator here. And I just wanted to point that out in case there was a question later. Okay, all right. So I defined the quantum framework that I'll be working in, and it's a natural question to ask whether the causal inequalities that appeared in the classical theory will survive in the quantum theory. Okay, and recall that in the classical theory, when we're dealing with these perturbations, we're allowed to restrict our attention to these graviton fields that are sufficiently small in amplitude, so that the combination is always Lorentzian. And so then we can use the theorems that we that had to do with Lorentzian geometry that demonstrated the inequalities. However, if such a restriction on the amplitude of H is not imposed, then this combination need not have Lorentzian signature. right? So it means that there may be results in perturbation theory if H is not restricted in amplitude that do not respect the causal inequalities that I derived earlier. Okay? And something like that happens in quantum theory. And let me show you how. So first, I need to define some technical idea I call a spectral density of a state with respect to an observable. Okay, if we're dealing with just a particle with 1 degree of freedom, and you think of the observable as x, then this quantity here is none other than the modulo squared of the wave function at some particular value x, which sits in the spectrum of the position observable. But if you have multiple degrees of freedom, this information does not capture everything about the wave function like it does for a one-dimensional particle, but it still captures the probability of being able to measure a particular eigenvalue A of a quantum observable A hat in the given state. Okay. So it's like the modulo squared of a wave function. When you consider all the information from it except probabilities of obtaining eigenvalues of a particular fixed observer. Okay, so if we had this spectral density for a particular operator A in a given state, then this actually allows us to compute arbitrary moments of the same observable given only this information. So it will just be computing classical moments of this probability distribution. And when we're dealing with the Fock state of linearized gravity or any linearized field, and if we're dealing with an observable, so this is going to be the Fock state here, and if the observable is a linear combination of the few degrees of freedom, then it's pretty easy to see that the spectral density is going to be Gaussian. Okay, just recall that the wave function, the ground state wave function of the harmonic oscillator is a Gaussian. So if we take a whole bunch of harmonic oscillators, the wave function is a product of all of those. That's again a Gaussian. And if you take the spectral density of some operator that is a linear combination of the harmonic oscillator degrees of freedom, then the spectral density is again going to be Gaussian. Okay, so this is exactly what happens here. The linearized correction to the emission time is linear in the field, the linear field with quantized. So if this is the observable that I'm trying to compute, whose spectral density I'm trying to compute in the Fock space, this Fock space vacuum, then I generically expect to have a Gaussian. However, note that the Gaussian has support everywhere on the real axis. But classical bounds on the emission time tell us that it can only take values between 0 and s. Okay, so fine. The Gaussian is peaked should probably be peaked inside this interval, but it still has shows us that the wave function has non-zero probability of giving, for example, a value for emission time that's much greater than s. Maybe a small probability, but it's still not zero. Same thing, the emission time for a particular absorption time, reception time s, there's a probability of getting it to have a negative value. So naively, one could say that these probabilities show us that there are violations of causal bounds in quantum theory, or causality somehow violated by quantum mechanics. But recall that the same exact thing could happen in classical perturbation theory if we did not impose bounds on the amplitude of h, of the perturbation h. So there's this unfortunate interference between perturbative effects and signatures of possible causality violations. So I mean, it's conceivable that once one quantizes the theory in some non-perturbative way, and one computes the spectral density of the observable in the particular state that would be chosen, you could have some probability leaking out of the classical bounds. That's not unheard of. Autonomy effects and quantum mechanics. But because of the weakness of perturbative arguments, any such effects at this level are masked by what are perturbative effects. So this is a bit of a cautionary example of trying to maybe make conclusions starting from perturbation theory a bit too early. So in this case, one of my motivations was to see what happened to causality in quantum mechanics. But unfortunately I discovered that I couldn't really make any strong statements about it. So that's the point of this discussion. Yeah.
So I think you said that your P of some observable will be Gaussian if the observable is a linear combination of the mode.
Yeah.
So is it true that you can write the time delay as a linear combination?
Right. So I mean, because I define this bit as a linear piece in the expansion, so it's then it's obvious. Okay. So let's see how much time I have. So maybe I should. So I basically already given the cautionary warning. So it's specifically applicable to if you look at the literature on quantum gravity, you find a lot of phenomenological work where people just start with the idea that there's some fluctuations in quantum systems, and then jump to the possibility that these fluctuations could involve the causal structure. So in the calculation I presented, one can explicitly see that this does happen, but that because of the methods by which the result was arrived at, one cannot actually make very strong conclusions about what happens at in the full nonlinear theory. Still, one can find a lot of phenomenological work based on these ideas. So, be skeptical. That's the main message of this slide. All right, let me show you a little bit about what happens when I try to do some explicit calculations. The first question is, what is it that needs to be computed? If I compute just the expectation value of this emission time observable, right, and I concentrate on the linear piece, the zeroth order piece is just what it is classically. But the linear order piece, like anything that is linear in the mode operators, has zero expectation value. So that's not very interesting. Right? Until we have something where you can study something at higher orders, there's nothing interesting in this expectation value. However, so this just tells you that the mean of this probability distribution is going to be at the classical level. However, it's going to have some non-trivial width to it, right? So it'll have non-zero variance. And the property of Gaussian is that once we know its mean and variance, we could know all other modes. So if you consider expectation values of powers of this quantity as interesting, then it remains only to compute this, the variance, and then we'll know everything from there. Right? So this is the thing that I want to compute. All right, what does the calculation look like? So the calculation looks like this. It relies on knowing the so-called Hadamard two-point function of the gravitational field. The Hadamard two-point function is the expectation value of the anti-commutator of the field operators. Just to show precisely what it is. So if I want to take this linear correction R and square it, and I sandwich it between two vacuum states, right, I can rewrite this as 1/2 of the anti-commutator in here. That's pretty simple. Then I recall that the expression for this correction R hat is actually it looks like some linear integral differential operator that depends on the background geodesics of this geodesic triangle that we started with, acting on this quantum field operator h hat. So what I can do is I can, from each of these components in the anti-commutator, pull out because the expectation value is linear, is a linear operation. I can pull out these linear integral differential operators, and then I have the anti-commutator of the field operators inside, which becomes the Hadamard two-point function, and then I have these complicated operators acting on this Hadamard two-point function. Now I have to tell you something about what these operators look like. Right. So I told you before that this expression has two terms. So this term h is the simpler one, and it's a sum over the three geodesics making up this geodesic triangle. And each term, which is denoted by an arrow here, has the form of a one-dimensional integral over the underlying segment of some components of the first derivative of the perturbation field. Okay? We check that h is invariant under linearized diffeomorphisms. The j term is similar but more complicated. So again, I'm summing over the three geodesic segments, and each term. So for each segment, I have two terms. So the term with a double arrow corresponds to something like this, where I have a single integral over the perturbation field with no derivative, and I have an iterated integral over a first derivative h, and then there's some extra terms that look like the ones that composed h, which come in this kind of funny sequence, which I won't really go into, but you can check the detailed formulas on the paper. But basically, what you see is that this integral differential operator takes integrals over one-dimensional subsets of Minkowski space, sometimes iterated integrals, and it takes at most one derivative of a metric, of the metric perturbation. If you know anything about the structure of two-point functions in quantum field theory, you know that they are singular as the arguments go close to each other. So the separation goes to zero or even becomes null, right? Because the Hadamard two-point function will look something like this. Well, when you look at these integrals over the underlying geodesic segments, then these arguments that you're integrating over, they often pass through each other or become null separate. So obviously, the divergences in this Hadamard two-point function will have to be somehow integrated over or dealt with in this expression. And it turns out that these one-dimensional integrals are not enough to tame the divergences in the Hadamard two-point function. So if you just naively try to calculate the result, you get infinity. Okay? In a similar way that you get infinity in perturbation theory in quantum physics. So what can one do with this? So my solution is to propose that instead of using, so here I've included just the usual point fields. So the metric perturbation field that depends on a particular point. My proposal is to replace these point fields by smeared fields. So instead of putting h hat here, I put here h tilde, where h tilde is a smeared and averaged quantum field around the point x. So and the averaging I do by a convolution with a certain smearing function. The smearing function you can presume to be strongly peaked at 0, and its width to have a characteristic scale mu that's smaller than all other scales in all the experimental scales in the experimental protocol. And for simplicity, let me just assume that all moments, all distance moments of the smearing function will behave like mu to the appropriate power. Now, why am I justified in taking smeared fields as opposed to point fields? I mean, is this an arbitrary replacement, or does it have some physical interpretation to it? I say that it has a physical interpretation to it. And to illustrate that, let me go back to an example that we can say we understand a bit better, which is of quantum electrodynamics. So forget about gravity, just think about QED or quantum optics, whichever one you're more familiar with. It's a pretty standard fact that if you try to, say, take a vacuum expectation value of the magnitude squared of the electric field at any particular point, you get infinity. Okay? Again, so the same issue as before. It's the singularity of the two-point function as the arguments go to zero. Separation between the arguments goes to zero. But if you first smear the electric field around a certain point, and then you square it and you take the expectation value, then you get some finite number. Now, what does this number represent? So this number corresponds to the variance of the vacuum noise, okay, the vacuum noise in the electric field in this particular case, that corresponds to the sensitivity profile of the detector that you use to actually measure it. Right? Because if you want to measure the electric field at a certain point to then be able to compute the variance of your measurements, then you need to put a physical detector somewhere in the vacuum. Right? This physical detector will never be able to tell you the electric field at a precise position at a precise time. It will always have some uncertainty built into it. Okay? So the detector will have some sensitivity profile. It will give you finite resolution space and time. And different detectors have different sensitivity profiles. So what this calculation tells you is that if you are in fact computing the variance of the measured field, which is smeared by the sensitivity profile, and you get a finite result, which is perfectly reasonable, but moreover, this finite result depends on the sensitivity profile. So the more sensitive your detector, the higher the noise. Right. And and this is actually a physical effect. So people who design diodes that measure photodiodes that measure photons are acutely aware of this. So they're always sources of noise. And if you bring your system to sufficiently low temperature, you don't have to only worry about thermal noise, you also have to worry about vacuum noise. So I think that the physical laboratory and probe systems they show similar effects. They are not point systems. They have some spatial extent, they have some temporal resolution in their measurements. So any measurements of the gravitational field that appear in this experiment will be of that smeared kind. Right? So one has to simply then pick a smearing function that will capture the physics of the way that these measurements are done. And the only way to do it is to have a sufficiently detailed model of the experimental apparatus that you're going to use. So I'm not going to go down that road. All I'll do is I'll just assume that there is some smearing function that is correct in this context, and the only thing I will need to know about it is this length scale mu, which tells me how big the moments, the length moments computed with respect to this smearing function are. And I'll call that length scale mu. And as a back of an envelope estimate for this setup, we can take mu as something like the wavelength of the signal that is being used to propagate the timestamp information from the emission time to the reception time. And here, I'll tell you precisely, I'll tell you a bit more about the assumptions I make on the smearing profile. I presume that it has, so I will presume that the smearing is actually point-like in the time direction. I presume there is no smearing in the time direction. There is smearing in the spatial directions, but that's going to be symmetric, radially symmetric. Okay? Unfortunately, when I say that the smearing is, there's no smearing in time direction, I need to specify which time coordinate I mean. Right? And I picked the time coordinate that's associated with the lab frame. An unfortunate consequence of this is that that time coordinate does not correspond to the natural time coordinate of the probe frame. And this introduces a break in Lorentzian variance of the calculation, which appears precisely at this point. And the reason I do it is because it's too complicated to do it another way. So I explicitly say this, but I hope to be able to come back at some later point and fix this. Yeah, but I have to make this assumption to make the calculation feasible. All right. So here's the quantity that I tried to compute. Here's a schematic expression for this integral differential operator. I have some tensor coefficients. I have integrals over geodesic segments, and I have differential operators acting on the metric perturbation field. Then I can write this smeared expectation value as a double sum over all these indices here, with the tensor coefficients taken out, and then all the integrals, expectation value, quantum expectation values, and derivatives packaged into these well, objects here, which I defined here. So the smearing, this double brackets correspond to the smearing, and the quantum expectation value appears here because this is the Hadamard two-point function. Okay, so I take the Hadamard two-point function. I need to compute certain double segmented integrals, and you take derivatives of them, smear, and then plug into this expression. Now I won't go into a lot of details of this calculation, but I can tell you that what's not so hard to estimate is kind of the dimensional analysis guess at how big the resulting expression is going to be, right? Just putting some dimensional factors into there, I can predict that there's going to be an overall L Planck squared factor in each term that come from the Hadamard two-point function. Then there's going to be a ratio of the scale of the experiment of the geodesic triangle to the smearing length. Right, so the smearing length, the smaller it is, the larger the result, so it appears in the denominator. But the denominator, the power in the denominator has a certain largest, has a certain leading exponent, right? So once one estimates the leading exponent, one can factor this out and then have an expansion in terms of the ratio of mu to s, which is a small quantity. Right, so what are the leading orders that we're talking about here? Right, so let's assign some dimensions to the quantities we're discussing here. So the smear length mu, the Planck length, and the space-time coordinates all have dimension 1. The derivative has dimension -1 because you write it ddz, right? The z is in the denominator. And then the expression for the Hadamard two-point function has this form where you have this is dimensionless, but it looks like the ratio of Planck length squared divided by coordinate separation squared. Right? And if you take the most singular terms from this expression, integrals soften the singularity, derivatives make it worse. So I take the largest number of derivatives, which is 2, and I take the smallest number of integrals, which is also 2. So if I apply derivative here to 1 over z squared, I get something like 1 over z to the 4th. Then if I integrate twice, I go from 1 over z to the 4th to 1 over z squared. So integrals change the dimension in this way. Or change the dependence on coordinates in this way, but then because the total dimension is fixed, I get some extra factors of squared here. These cancel, take L Planck out of the smearing, and the smearing of 1 over z squared gives me something that's of order 1 over mu squared. So the result is that this quantum variance is going to behave like L Planck squared divided by mu squared. So notice this effect that I mentioned before, that if the resolution of the detector becomes better, so mu shrinks, the vacuum noise increases. And this shows you that the increase goes as 1 over this mu length squared. In more detail, once you factor this thing out, you get the following expansion in powers of mu divided by s. So these are small quantities. So one just needs to compute these coefficients rho 0 and rho 1. Unfortunately, you notice that so there are some correction terms that I haven't included, which have the same order of magnitude as the leading order coefficient here. And the reason for that is that I only computed the linear order expansion of the emission time, right? But I'm computing the variance, the quadratic expression. So if I really wanted to be consistent, I would have to compute the quadratic correction to the emission time and include that in the calculation. But that's even more complicated, so I haven't done it yet. So that's something done for the future. But if you just consider the linear order correction that I computed, then square that and take the expectation value, this is the structure that you get. Just to give you an idea what size of the fluctuations you should expect, the unfortunate thing is that everything is damped out by a factor of Planck length here. This Planck length is very small. So if you put in all the units and estimate the root mean square fluctuation in terms of seconds of the observation of the emission time, you'll find that in different scenarios you can get different answers, right? Because you can have different values for the experimental scale S and the smearing scale mu. So if you consider a laboratory example where, say, you're dealing with spatial separations that are order of meters, and you're using signals that are, say, of X-ray frequency, then the fluctuations size, RMS fluctuation size you should expect is 10 to the minus 35 seconds. So that's definitely way beyond the threshold of detectability, but recall that the idea behind this is not necessarily to find something that will be directly testable, but to hone our skills in computing some gauge invariant gravitational observables and quantum corrections. In cosmological context, if you have a geodesic triangle that's on the scale of separation of galaxies, about 1 or multiple megaparsecs, and just for the heck of it, keep X-rays as setting the smoothing scale, you get fluctuations of order of 10 to the minus 12 seconds. And this will grow with the separation scale. So this predicts that for very distant light sources, you get a lot of fluctuation in the reception time. But still below our detection thresholds, and the cosmos is a very messy place. So there are many things that will appear along the way and influence essentially the same observable, this fluctuation in the reception time. So I don't know if there's any particular hope of observing something like that in the near future, but something to look out for. Right, so let me tell you about these coefficients, the rho 0 and rho 1 coefficients, which is only that you need to know to figure out what is the size of this quantity and how it depends on all the other parameters. I mean, the basic parameter that I haven't mentioned yet is the relative velocity between the laboratory and probe bohr lines. So here's what this plot shows. So the horizontal axis is the relative velocity, and the vertical axis is the rho 0, which is a pure number coefficient. And it's been computed recently in collaboration with a master's student in Utrecht, Beatrice Banga, who finished her thesis in the summer, and we're working on writing up her results in a paper that should hopefully appear next few months. And this plot was produced by so it was computed not symbolically, but numerically, so to speak. But it so happens that all the calculations involve only rational numbers. So if you take rational velocities, then you get essentially a rational number for this coefficient here. With, well, there are a few logs that appear, but the arguments of the logs are also rational. So we expect this curve here to be a rational combination of the relative velocity and a logarithm with rational argument, rational terms of velocity. And the rho 1 coefficient is just always a constant. Interesting observation, we don't really know what the significance is. What is interesting here is that the result appears to blow up at low relative velocities, which we also find very puzzling and don't really have an explanation for, because this means that if you have two objects that are very close to each other and are essentially not moving with respect to each other, you expect to see huge fluctuations in the reception time of the signals sent between them. I don't know if that necessarily matches with what we see in everyday experience. So there's a question mark here about how to interpret this. It's possible that that term that appears here that's of the same order, its dependence on the relative velocity may influence this divergence, but we don't know yet. Right? So now let me conclude. So, so I've discussed how it's possible to construct very reasonable diffeomorphism variant observables in classical and quantum gravity by considering thought experiments and the corresponding physical interpretations associated with them. I showed you that time delay is a particular example of such an observable, and that besides being an example, it's also sensitive to the causal structure of the ambient spacetime where the experiment is performed. And I don't think it's very hard to come up with many other examples that are constructed in a similar way. You could have a different geometry for the laboratory and the probe. You could have multiple probes. You can have different ways of them changing their velocities. So you could have not just triangular geometries. You could have more complicated ones. And I think it's worth thinking about this class of observables. So to promote that, I came up with a specific name for them. I call them quantum astrometric observables. So feel free to come up with your own examples. The calculations I presented are all based on perturbation theory. Unfortunately, this is the tool that I'm most familiar with, and it's even close to state of the art when we're considering the quantum theory, at least in 4 dimensions. In 3 dimensions, there's a wider range of techniques that allows us to do calculations in quantum theory. So it's possible that in 2+1 gravity, and we have at least one expert in the audience, it might be possible to do some non-perturbative calculations and make stronger conclusions about what happens to the causal bounds that I've established classically for the time delay. So unfortunately, this exceeds my expertise.
Catherine Weisberger has done all of the foundations that should be necessary for that. She's done all of the calculations of time delays.
So I have talked to her about this,
Yeah.
and so she's only done it at the classical level. So
Right.
that's one thing.
Yeah.
And I asked her if she was interested in doing the quantum version.
Mm-hmm.
And unfortunately, the impression I got is that her interests were drifting in some other direction. So it's unclear when or if ever this would actually be computed. But I'd be very curious.
Yeah.
Yeah.
The classical observables are known.
Yes.
Basically closed form,
Right.
more or less. So.
Yeah. So if there's any expert in 2+1 gravity who finds this interesting, I'd be happy to talk about it. All right. Some questions of outlook. I mean, I did stress that it's easy to come up with examples of observables if I include some matter in the description, but maybe it's not as necessary as one as might appear at the surface. So maybe there is a way to define geodesics that don't depend on matter content, but maybe on some asymptotic structure. So one can find some references to papers from Homar and Bergman that discuss this idea. Another question that's interesting for me is to generalize, to come up with an example of something like a quantum astrometric observable that will tell us something about not just Minkowski space, but also another geometry like cosmology or black hole. So for example, could there be an observable of this kind that tells us something about the size of a black hole? And knowing that, would it be able to tell us something about how the black hole evaporates in a dynamical way? So that's something I would like to think about in the future. So with that, I'd like to thank you for your attention.
Questions?
Yeah.
So if I understood correctly, are you not accounting for the classical gravitational field of your experimental apparatus?
No, so I'm excluding that reaction. So the reason for that is that, I mean, we are massive classical objects, but you can neglect our back reaction, you know, to this room or the workings of our clocks and so on. So in some limit,
Yeah.
I'm presuming that the experiment is done in some limit where these are negative.
I have a comment and a question.
Okay.
The comment has to do with this problem that even classically you risk getting signature change if you do linearized gravity.
Yes. Yeah.
There is an old standard way out of that that I think was probably first introduced by Isham, which is that if you take as your classical observables a tetrad rather than the metric,
Yeah.
then it doesn't matter how large the fluctuations
Yes,
of the tetrad
that's a very good
are.
point. So you could parameterize all Lorentzian metrics by taking a tetrad, right, and then acting on it with arbitrary general linear transformations,
Yeah.
right? So that preserves the signature of the metric.
Right.
And I've actually considered doing calculations in this way. I mean, you could write, instead of writing g is equal to eta plus h, you could write g is equal to some so eta and acted on by linear transformations, right?
Mhm.
And you can write the linear transformation as something like this, right? And this quantity can be unrestricted.
Mhm.
And in fact, you can get quite a long way using this expression, because even if you promote this to a quantum field, right, there are standard formulas for computing vacuum expectations of exponentials of linear field operators. Unfortunately, the calculation was sufficiently hairy without introducing this that I never went that far.
You can do it more simply than that.
Even more simply. I mean, you
You
mean the
can
Cayley
just-
calculation?
Yeah, no, I mean, you just write your metric as and just like that.
Yeah.
And then do ordinary Fock quantization of your h's. You don't need exponentials. I mean, this is still, classically, that's going to remain Lorentzian no matter what h is.
Okay, that's a good point. Yeah, thanks. I haven't considered that.
So, I mean, then the sort of the linearized quantization
Okay.
is exactly the same. You just have,
So the observable will be
you have an
different.
extra
Yeah.
gauge symmetry, local Lorentzian variance you have
Yeah.
to fix. But,
Well, what this changes is it changes the expression for the observable when you
Right.
expand.
yeah,
However, from what you wrote here, I see that
I guess
the difference will appear at quadratic order, which I haven't computed anyway. So
oh, okay, yeah, that may be true.
yeah,
Yeah.
but it's actually it's a good point. Yeah, I haven't thought of it.
Then the question is whether if instead of smearing orthogonal to the world lines. Can you control the divergences if you just smear in time?
That's another very good question. So I'm not the only person who has considered these kind of observables. So there's a slide that I skipped over where I had some extra references. So Larry Ford has looked at these kind of observables as well, and his work inspired others. So me indirectly, because I only learned about his work a bit after I started considering similar ideas. But there's also a pair of people who were inspired by Ford's work and wanted to tie up some loose ends. So that's Albert Rura and Daniel Arteaga, where unfortunately neither of whom is now working gravity anymore. So it's unclear whether their unpublished work will ever see the light of day. But having talked to them, they did many things that are similar to what I'm doing. But almost everywhere where you could make a different choice, you made a different way. So in particular, instead of spatial smearing, they did use time-like smearing. And it appears that it did work as well. Okay? So, but of course you get different functional, or different expressions in the end. So I haven't done that myself, but it still doesn't solve the problem completely because it's still not completely clear how to smear the null geodesics, because there's no scale on the affine parameter.
Right. Okay.
But it's something else to think about.
Because, I mean, when you said that you're neglecting the quantum fluctuations of the clocks themselves,
Yes.
but if I remember Salica and Wigner correctly, in order to do that, you have to assume that they're very massive.
Yeah.
And so then you get classical back reaction.
Yeah.
If you think of them as light clocks, then you automatically get smearing in the time-like
Yes, that's right,
direction,
yes.
but in a way that I think ought to be,
Yeah, you can just incorporate it into the smear.
just stick that right in and
Yeah.
have some immediate physical
Yeah.
meaning.
So I would love to be able to do smearing in all four directions. But it does make the integrals that appear more complicated. So I haven't spent enough time to think about how to get around that. So I think that would be optimal because then it has even more possibilities, incorporates more physical effects.
Any other questions? Well, let's thank our speaker again.
Thank you.